You are made of atoms. But atoms are not the bottom. Inside every atom is a nucleus. Inside the nucleus are protons and neutrons. Inside those are things smaller still. Eventually, you hit particles with nothing inside them. No layers. No substructure. Just particle. The standard model is the full list of those particles. 17 of them. That's it. That's all the stuff the universe uses. First, a fast orientation. Atoms have 3 parts you already know. Protons, neutrons, electrons. But protons and neutrons are not fundamental. They're built from smaller things. Electrons, by contrast, are already fundamental. Nothing inside, just electron. Okay, quarks? A quark is a fundamental particle. There are 6 types. They come in pairs, ordered by mass. First pair, up and down. These are the important ones. Every proton is 2 up quarks and 1 down quark. Every neutron is 2 down quarks and 1 up quark. That's the entire nucleus of every atom in your body. Up quarks and down quarks shuffle differently. Everything else in the universe is just these 2 quarks making decisions. Second pair, charm and strange. Heavier, unstable. They exist briefly, then fall apart, like a coworker who shows up, microwaves fish, and immediately quits. Still part of the team, technically. Third pair, top and bottom. Even heavier, even less stable. The top quark weighs as much as an entire gold atom, except it's a single particle with nothing inside it. Nature made this choice without explaining itself. Now here's what quarks cannot do. They cannot exist alone. Quarks are always locked together, held by something called the strong force. Try to pull a quark out of a proton, and the force gets stronger. It doesn't break. It just stretches and snaps back, sometimes creating new quarks in the process. Quarks come bundled, non-negotiable. The particle that carries the strong force is called a gluon, named after glue. Physics has occasional moments of accidental honesty. A gluon's job is to hold quarks together inside protons, and protons have survived for 13.8 billion years, so gluons are good at their job. Better retention than most startups. Next, leptons. Leptons are fundamental particles that don't feel the strong force, not made of quarks. Their own category. 6 of them. 3 pairs. First pair, electron and electron neutrino. The electron does all of chemistry. Every chemical bond, every molecule, every cell in your body. Electrons. The electron neutrino is the electron's nearly invisible partner. Almost no mass. Barely interacts with anything. Right now, about 100 trillion neutrinos are passing through your body per second. They don't notice you. You are not an obstacle to them. You are scenery. Second pair, muon and muon neutrino. The muon is basically an electron, but 207 times heavier. It's unstable. Lives for about 2 microseconds, then decays into an electron. Nature made a second electron. Heavier, worse, unrequested. It showed up anyway. The muon neutrino travels with it. Also barely interacts with anything. Also does not care about you. Third pair, tau and tau neutrino. The tau is even heavier than the muon. Lasts about a picosecond, 1/trillionth of a second. It's so brief it's almost a rumor, except it keeps showing up in detectors. It has a neutrino, they both exist. The universe keeps making these things, and nobody fully knows why. So now you have 12 matter particles, 6 quarks, 6 leptons. This is the stuff that makes up stuff. Physicists call them fermions. Don't worry about the name. Fermions are the matter. Everything else is the forces. Forces. Every force is carried by a particle. Not a metaphor, an actual particle. These force carriers are called bosons. First, the photon. The photon carries electromagnetism. Light is made of photons. But photons also carry the electric force between charged particles. When 2 electrons repel each other, they're exchanging photons. Same particle, 2 jobs. No overtime pay. Second, the gluon. Already mentioned, carries the strong force. Holds quarks inside protons, and protons inside nuclei. Without gluons, all nuclei dissolve in nanoseconds. You dissolve with them. Gluons are doing a lot of work and asking for nothing. Third and fourth, the W boson and Z boson. These carry the weak force. The weak force handles radioactive decay. It can change one type of quark into another. A down quark becomes an up quark. A neutron becomes a proton. This is how stars burn. Nuclear fusion in the sun depends on a weak force flipping quarks around. The W and Z bosons were predicted in the 1970s and found in 1983. The weak force is misnamed. It's not weak, it's short range. That makes it look timid in experiments. It isn't. So, 4 force carriers: photon, gluon, W boson, Z boson, 4 forces, electromagnetism, strong, weak, and gravity. No gravity boson in the Standard Model, no particle for it. There's probably a graviton, a force carrier for gravity, but nobody has ever detected one. Gravity just sits outside the model, the most obvious force in your daily life, the worst understood at the particle level. The Standard Model simply does not include it. We'll come back to that. First, the Higgs. In 1964, physicists predicted a new particle connected to a field that fills all of space. In 2012, they found it, the Higgs boson. The Higgs field exists everywhere, at all times. Every particle that has mass gets its mass by interacting with this field. More interaction, more mass. Photons don't interact with the Higgs field, no mass. Move at light speed. W and Z bosons interact a lot, very heavy. Top quark interacts more than anything else, heaviest matter particle in the model. The Higgs field isn't giving particles mass out of generosity. Think of it as resistance. The particle moves through the field pushes back. The pushback is mass. Before this field switched on, a tiny fraction of a second after the Big Bang, most particles had no mass. They moved at light speed. No structure, no atoms, no chemistry. Then the Higgs field turned on. Particles slowed. Mass appeared. The universe could now build things. It took about 380,000 years to build the first hydrogen atoms. Another 13.8 billion years to build you. The Higgs field started that entire chain. Finding the Higgs took 50 years and a machine 27 kilometers in circumference. The Large Hadron Collider smashes protons together at near light speed until things fall out. The Higgs boson was the last predicted particle of the Standard Model to be confirmed. Every other particle had been found before 2012. The Higgs held out until they built the biggest machine in human history to look for it. Found it. The jigsaw puzzle, started in 1964, had one missing piece. They found the piece. So that's the model. 12 matter particles, 4 force carriers, 1 Higgs, 17 total. The most successful scientific theory ever built. It predicts particle behavior to 1 part in a billion. Tested constantly, consistently, right? Kind of embarrassingly right? Here's what it gets wrong. Gravity. The Standard Model describes 3 of the 4 fundamental forces. Gravity is absent. Every attempt to add it breaks the equations. This has been a problem for decades. Still a problem, dark matter. About 27% of the universe is dark matter. It has gravity. It holds galaxies together. It is not in a Standard Model. Not even a placeholder. Whatever it is, it doesn't interact with a photon. You can't see it. No one has directly detected it. It doesn't match any particle in the model. Dark energy. About 68% of the universe is dark energy. It's driving the accelerating expansion of space. Also not in the Standard Model. Also completely unexplained. So the Standard Model covers about 5% of the universe. The other 95% is labeled none known and currently winning. This is not a failure of physics, it's a success with an honest boundary. The Standard Model is extraordinarily accurate for what it describes. It just doesn't describe everything. It's a perfect map of one city. Turns out the city is on a planet, and the planet is inside something much larger. And we don't have that map yet. So what did we learn? Matter is made of fermions, 6 quarks, 6 leptons. Forces are carried by bosons, photon, gluon, W boson, Z boson, Z boson. Mass comes from interacting with the Higgs field. The model is accurate enough to build particle accelerators, predict nuclear behavior, and explain all of chemistry. It doesn't cover gravity, dark matter, or most of the universe. Nobody agrees on what comes next. 17 particles, 3 forces, 1 Higgs boson, and 1 very large question mark that physicists have been arguing about for 50 years. That's the Standard Model, all of it. Well, almost all of it.